Good morning to everyone on the West Coast, good afternoon to everyone on the East Coast, and good evening to everyone in Europe. Welcome and thank you for joining the Neo4j webinar series. My name is Adam Frankel. I am the host of our webinars, and today we'll be talking with Peter Neubauer and a special guest about Neo4j in real-world scenarios. Let me first introduce you to the GoToWebinar software. On the right part of your screen is the GoToWebinar control panel. During the presentation today, you'll have the opportunity to ask questions. Please feel free to type your questions into the question box. We will attempt to answer all of the questions during the webinar, maybe not immediately if we see the questions will be answered by a follow-up discussion. If we don't get to your question during the webinar, we will follow up and answer you afterwards. Now, before you start typing in, I already know what the most commonly asked question is going to be. It's, are you making a recording of this webinar and can I get access to it? And the answer to that question is yes, we are recording this webinar, and after we have uploaded it to our servers, the link to the webinar will be available from the neo4j.org website. Let me now introduce Peter Neubauer, one of the founders and the Vice President for Product Management for Neo Technology. Peter, please take it away.
Hi everyone. You can't hear me, and I can see you because I have a full screen display here. We're trying to start off here with a webinar that is very, very high level, which is that I would like to show you where we see a lot of interest for graphs and a lot of ideas and interesting stuff going on, just to give some inspiration to everyone that might wonder what graphs are used for. And also, I invite you to share what you are doing. I know there's a lot of our good friends and customers in this webinar, and it would be awesome to partly get questions for you and from you and get a overview of what you are doing with Neo4j and graphs, or what you're thinking of to do something. Also, there is a number of people from Capgemini joining this webinar today, mostly because of not only that Neo4j is awesome, of course, but because of Julom. Julom Ali is a software architect at Capgemini in southern France and has recently been discovering and trying out Neo4j. Maybe you can say a few words on what you experience, what you find, and what you're using it for. Julom.
Yes, hi all. So basically what I used Neo4j for, I had a client which
It seems the internet connection is a bit slow here. Adam, can you hear me?
Yes, I can hear you, but I think that Jalami's audio connection has disappeared.
Okay. Maybe we can wait for Jalam and I just carry on.
Sure. Why don't you carry on, and Jalam, if you can hear me, why don't you try reconnecting, and we will bring you back into the webinar in a few minutes.
a product struct he wants.
Jalam?
Yes.
Your audio cut out completely from the beginning. Would you mind restating what you said from the very beginning?
Yes. Okay, so my client, he had a props stored in an RDBMS, and he was facing performances problem for traversing his graph, because RDBMS are not made for that. So I think why not using Neo4j for that? And well, I'm only at early stages of evaluating the solution, but it looks promising compared to RDBMS for traversing big graphs.
Sounds good. We won't share too much of details about that, but we're still working on it, and it's looking very promising. Basically, it's deep trees that we are trying to traverse there. But I will say more about that in other scenarios where we have deep hierarchies that we are trying to connect. So let me thanks, Jilan, for the brief intro on what you're doing with it. Let me just start. Maybe a little background introduction. I think many of you know this. Of course, there's a lot of data out there, and it's growing. And the whole data size and data complexity movement has resulted in a number of different approaches to manage this. On the data size, we have the key value stores, all part of the big NoSQL movement that has been popping up since 2009. That are basically trying to take the key value approach and shard and scale along very small data entities called the keys and values. So it's basically distributed hash maps that you're dealing with, and then you do a big map reduce jobs over them. Then we have the big table clones that are a bit more complex. They're also called column stores that can handle several different areas of aggregation, like time and column and row. And then we have the document databases like MongoDB and CouchDB that are taking the document, or like a hierarchical substructure, as the base entity of the data model. And then we have graph databases that are modeling the complete data structure to its largest extent, and then do very complex and deep traversals around this. Now, that said, it looks like the data size is decreasing here. What we see in practical scenarios is that graph databases, especially Neo4j, can handle a lot of these requirements. Our biggest installations right now are around 4 to 10 billion relationships, which is still handleable on an uncharted graph. And of course, when you then shard, you get a superset of that, and that is good for a lot of use cases. Of course, there are others that need to be done. What we see in practical scenarios is that high availability and operational security is far more important than the sharding approach. Sharding is important when it comes to handling write loads, but there is a number of ways to do that. So let me just go on. So what is Neo4j then? Neo4j is an open source Java implemented graph database having its own storage format that is optimized for handling relationships and nodes. Basically, all these data structures are interlinked on the storage level, which means you can act very lazily on queries that don't touch the whole data store. It's both available as an embeddable Java library and server-based, where you interact with it REST-based. We are thinking and working on a binary protocol that will probably make it into 1.5 that will be much higher performance than REST-based approaches. You combine the graph engine Neo4j with an index framework, and thus you have the possibility to both use global indexes in the graph that otherwise are not super efficient in graph structures, and of course the main issue that is the shining point of graph databases is the index-free traversals of data, both in the caches and on disk level. So you get like good performance out of your queries if you structure them in a way that is optimizable by a graph, which is of course a challenge since the whole field of graphs is in production is quite new. Of course, in theory, it is quite old. So there's there's a discrepancy between what is used nowadays in production and what is there in theory on exhaustive graph algorithms, which mostly don't scale. It is fully ACID and JDI like transactional compliant, which is a bit of a different to other NoSQL databases, since we really like to have the data stable and persistent and recoverable. As I said, there's a transactional indexing framework. Usually we work a lot with Lucene. Lucene has good performance even in big data scenarios. Recently have been working a whole bit with Redis, which is about as fast as Lucene. It scales to even greater data amounts. From the speed perspective, actually, an index that is configured as exact in Lucene is about as fast as Redis. So that's quite interesting. Neo4j has been in production since 2003. We recently added high availability and clustering support, which now is in production at several sites. And we have a great community that meanders into a lot of other communities also. And there's a number of interesting bindings that make working with graphs a joy. They are like very object-oriented bindings in JRuby. There are REST-inspired bindings, there are procedural bindings, and there are Groovy bindings and Gremlin bindings that are optimized for graph traversals. You can pick and match what you want to do. We also have integrated into Spring Data for annotation-based access to the graph, so you don't have to write any mapping exact annotations on Java classes. We will be having a webinar about this in the future, maybe even before summer. We are currently working with a lot of cloud deployment. Amazon Web Service is one of the big ones. Azure, Microsoft Azure. Cloud Foundry is right now being debugged and shipped, and Heroku is on its way too. It's in beta right now. So the core abstractions, let me just go through this very brief. I think that is quite known to you. It's node relationships and key value properties on these that are schema free, so you can do anything you like. It's like hash tables there. There's no types on nodes. There's types on relationships, which really is a propagated level, a label that is stored together with the relationship. So you have like basic typing in the graph. In Ruby, interacting with Neo4j, for instance, looks quite straightforward. You install the Neo4j Ruby gem, then you require it. You make a class that includes a Neo4j mix-in that makes the magic, and then you declare properties on the person object, name, age, and occupation in this case. Then you have an index that you put on a property that then will auto-index this property, and you declare a one-to-many relationship of friends. So this is your kind of type system. If you want that, you can also use, of course, the raw API that is absolutely non-typed. So now you create two persons, Neo, which is a person that has a name of Neo and an age of 29, and Morpheus, which has a name and occupation. So you don't need to specify all the properties that you have set up. And then you simply add Morpheus with a friend relationship to Neo. That's it. So it's very straightforward. You do that. Oh, there's a transaction is wrongly spelled. Sorry for that. You do that in a transaction, and you traverse then the graph outgoing from Neo along his friends, and you just say .each and have a closure that prints them out. So this is the kind of traversal approach. I'm not going deeper into traversals right now. We will have a webinar with Marco Rodriguez talking about like Gremlin and different types of traversals, and we will probably have a webinar on the Neo4j traversing framework too. So that is for another time. Neo4j 1.3, it became GPL, which is much friendlier to everyone using it, especially in web stacks. we went up to 128 billion primitives, and we're using actually some of that already. Spring Data integration became stable. We made some optimizations in the storage layer. The web visualization is coming along, and now you can do server plugins for moving the code to the data, since REST inherently is quite slow if you have high performance scenarios. And high availability that was introduced in 1.2 got a bit of a shape up and will be even more shaped up now in 1.4. So high availability in Neo4j, how does that work? Basically you have a zookeeper service here in the lower end here, a number of zookeepers that balance each other and provide failover on that level. And then you have a cluster of Neo4j databases that are in contact with each other and choose and elect a master automatically. Now you can write to any Neo4j slave instance, these upper levels here, that will take a lock on the master and write to both the slave and the master before committing. And then after that, the master mirrors out, or the slaves are pulling updates from the master to update themselves upon requests or upon scheduled intervals. That means you can do, with this setup, read balancing, read scale out. You can also do failover, since a failing master is automatically replaced by one of the slaves becoming master automatically. And even if there's a number of different scenarios that can happen if a machine goes offline and online and so, but that is all handled by the AJ cluster. So that is the basic setup that makes for 24/7 several 9 installations. So what do people with Neo4j? That is the point. I wanted to just mention for you today a number of cases where we see graphs being used, and that might both inspire you and give you some questions on how these installations are doing and how people accomplish this, and that is what I would have your questions around. So let me just mention briefly before we dive into it. Normally we have big amounts of complex and connected data in different domains that people use Neo4j for. Normally that is more than 1 million nodes or relationships or properties. That means you're actually placing a bit of a load on the machine, and handling these things becomes a problem in relational databases. Apart from the fact that, of course, development time in graphs is much nicer, and it's much easier to interact with graphs because they're very, very whiteboard friendly. Also, one of the criteria when you want to use Neo4j is when you are in need of real-time analytics on real transactional data. That means we're targeting response times that are far lower than 1 second, normally in the between 1 and 20 milliseconds range, with the answers, and then real-time load. That means in some installations there are like thousands of requests on Neo4j traversals on one machine, and then you want to act on the real data. That means you don't have a analytics store that makes things up overnight or so, but you want to react directly on things that are changing as your system is doing transactions. Now we will look briefly at a number of different scenarios. One is network and cloud management. One is master data management. One is social applications and recommendation techniques. One is finance and insurance. And one is spatial things, geolocation services, and others. And then, of course, there's a number of other applications that all of you are doing probably, and so I can't really say all of them, and of course that's also due to privacy of our customers, and so we can't really disclose everything. So yeah, for instance, content management system, customer relationship management, that is actually an area where Neo4j comes from. The first thing we did when we implemented Neo4j was that we had a content management system with a number of complicated customer relationship management rules, who could see what, and so on. That led us to actually employ a graph for this. Bioinformatics and genomics is something that is very, very interesting. There is a number of ontologies out there, like SNOMED and others, that need to be brought together and analyzed. A classic thing is the transformation paths of chemical substances and genes, by which you can transform things into other genes, and that is basically big graph statistics. Semantic applications like RDF are very common on Neo4j through different RDF layers, both Neo4j's own layer and the Tinkerpop sail layer, which makes RDF be projected into the property graph model of Neo4j. And then, of course, all forms of intelligence applications where you look for patterns or call clusters or mail clusters also in big graphs of communications and other forms of interesting data. Now, let's look at this, impact analytics and network management. Basically, network management means that you're managing topologies of physical or logical things. It looks roughly like this. You have, this model is mostly a physical ontology, physical topology. You have here power generators, and you have a number of servers that are powered by these power generators, and then you have instances of virtual machines, and then you have logical applications that might run on these machines, on several of these machines. For instance, database clusters or so, and probably have, like, farther down even more high-level things like user interfaces and so on. Now, what you want to do with this is a number of things. These form a very big graph in a data center. Depending on what you do and how big it is, you can easily end up with 500 million relationships between these elements. And then what you want to do is to really fast and real time find out if the power generator 1 goes down, what does that mean for this data center or for this network? Which applications or which servers will be affected? In this case, server 1 will be affected and server 2 will be affected. And which applications sit on instances that are affected? The blocktastic application is directly down because it only runs on an instance that is powered by that generator. The big media application might decrease in throughput by 2/3, and the third application is not affected at all. So what you do there is to have something called impact analytics that propagate the fault of the power generator along the network and along propagation functions to alert that the blocktastic application is totally down because the impact from the power generator through the network is very, very high. You basically check, the server here gets a very high fault behavior because it is only powered by one generator. Then the instance here gets an even higher fault factor, and then the application here also. Same thing happens with server 2 and instance here, but here the propagation is not as big because there's 3 instances powering these applications. This is one thing, to alert the users, and then the next thing is to determine where do I have to redeploy this application so it is both in a working instance and on a working infrastructure, and it is not infringing on other, say, vendors that are hosting the data on this data center. So you have virtual data centers that might be hosted by or rented by PepsiCo and Coca-Cola. So you don't want to interfere with their applications. So you have all sorts of rules there. Another application for this is, of course, to find out what does the network look like right now, both from documentation perspectives. You want to find out, like, is there a port free on the switch that is connected to this server, and also from a security point of view. Can I get from a server that is the server 4, for instance, that is compromised by an attack? Is there any way I can go through software to my application here in the bottom left? And that's a security implication. There is actually starting to emerge standards that prescribe how applications have to be secured in cloud deployments, and to enforce these rules, right now you have to manually inspect all the applications. That's a huge job to draw these conclusions. So that is something that you can automate with this network approach. And of course then in real time see, oh, this is compromised, what does that in security impact analytics mean for the applications? Another area of interest is, for instance, the provisioning of new applications that mean you find spare resources and the needed resources to provision when you deploy something new. In real world, this can look like this. This is a very, very small example of just the physical structure of a data center. You have the data center logically here in the middle, and it has like a number of computing resources, and it has blade servers up here, and it has hypervisors that power virtual machines. And then you have, switches and firewalls and Ethernet ports and everything, and even storage arrays attached to this. So it's quite a big challenge to do this, and in many queries, the data locality here is of importance. You only want to find out what is around a certain node or some certain nodes. So that is that form of network management that we see frequently. What also is a very interesting and not obvious application of graphs and of Neo4j is the whole master data management area. Master data management means that you are holding like the core of your data in one place, and then you try to massage it in different ways to make relevant views of it. Here we, for instance, have an example of customer master data management. Customer MDM means that anything connected to the customer or the sales representatives or the sales of a company is represented in this system. And normally this means you have a number of different hierarchies that need to be at the same time traversed and connected. In this case, it's 6 hierarchies. You have, for instance, here the CRM, the customer relationship management, who is handling this customer, and so on. Then you have a sales hierarchy. The sales team has sub-teams, and they form subgroups, and so on, and they might specialize in different areas. Then you have geo-boundaries, which are like natural boundaries, like continents or regions or so. Then you have political boundaries that are countries, zip codes, and so on. And they might overlap or not with the geographical boundaries. And then you have the customer organization, their headquarters, their branches, and so. And then you have the whole security layer that intersects all this. and altogether form something called, for instance, a sales view that might be something like show my accounts of all U.S. headquarters subsidiaries that are in my sales area, for instance, San Francisco and Los Angeles. That means you need to find out like what are the relevant things. When you look into that in the Neo4j web admin, we modeled a very, very small subset of this. You see actually the different trees here. You see 4 of these trees. So you have the geo like beginning of that hierarchy here. You have the political hierarchy here. You have the customer hierarchy here, the corporation, and then the headquarter and the branch. And then you have the sales and ACL kind of collapsed hierarchy. So what you want to do is to find out like how can I best intersect all these things. In relational database, this would mean to crunch a lot of joins to find out what we just said. In bigger customers, only the branch offices here can be like 20 million records. That means there's a lot of data to crunch if you do it globally. In Neo4j, you actually pick a branch or you pick an area, and then you go up and check the area, you go then and check the branch. From these you go to up the sales team and check there, and you might even check the geo boundaries. These are all traversals that are at most like 4 or 5 hops away, which means you can via smart exclusion and inclusion get down the query times from like minutes to milliseconds, which is a very, very relevant improvement. And of course, you can do very much more complex things on live data. Social graphs is probably what everyone's thinking about when they hear graphs. The normal social graph is not really a social graph. It's a graph like that is partly social, but it is also, for instance, tagged. There are tag hierarchies. There's time components, and there's geo components here, which might be where people live. And so again, there's a number of different indices being linked together. The typical things you want to do with a social graph is recommendations, different forms of recommendations. I will say something to that too. You want to do location-based services, whether with Neo4j Spatial or not. You want to find out local influences in communities, which might comprise to explore the vicinity of some starting points. A normal operation there is also the shortest path operations that, for instance, are capped by a certain length, say 4 or 5. Another interesting application is to have live views of a community or of your social environment or your relevant things aggregated in social dashboards. So you can find out like the mean characteristics of your community or your area of relevance. The focus here is that this can be run on actual data in actual time. We have installations where we run in less than 20 milliseconds, in less than 1 millisecond, with a traversal speed of about 1,000 nodes per second, 1,000 nodes per millisecond. So that means in a millisecond you can touch 1,000 nodes and find out relevant things. Or if you have like 20 milliseconds, you can touch 20,000 nodes. You do that on an 8-core machine. That means you can serve 1,000, 2,000 requests per second on a single machine, which is like real production load, which with response times of under 20 milliseconds, which then makes it feasible to do it in real time. Recommendation engines are very, very increasingly relevant. We will hopefully have a seminar with Marco Rodriguez on recommendation engines, because he has a lot more material on this. But basically, Nova Spivak has been saying that the 90s were the web of browsing, the 2000s the web of search, of the big search engines, and what we are now approaching is the web of recommendation, where you use systems and your social network to filter the information for you and to recommend what to look at and what not. This is not only true for personal recommendations, but even for e-commerce, for advertising, and then of course for friends and interests and places, partners, yeah, a lot of things. Basically anything we can think of is increasingly being influenced by recommendations from different parties. When it comes to techniques, there's of course data global techniques like pre-calculating things, or calculating averages and histograms and statistics on the global mass of things that you want to compute on, like previous purchases and so. But what we see is coming up really as a value-added proposition is data local techniques. One of these are of course heuristics. PageRank is a global heuristic that explores around random starting points, locality of data, and looks what is the most highly ranked web page in a very narrow area. And then we have local recommendations, where you have a number of different things, like shortest path, of course, that explore, like from 2 or more endpoints, how can I reach these things? Not only the shortest path, but for instance, all shortest path, or all paths that are possible in a given or shorter length. You have hammock functions that basically extract strong links around a network that is weakly connected. The Netflix recommendations are running with this. So if you find paths that share nodes between 2 points of interest, for instance, between a movie and a person, and they're connected by more than 3 other nodes in between, like purchase or other friends that have seen this also, then you make the deduction that this is a strong connection, and by that you can derive higher order relationships that are strong connections between things, and by that reduce the amount of and strengthen the amount of recommendation you can do. Random walks and energy diffusion is the technique of sending probes around certain points of interest into the network, and then make them walk along certain patterns, certain relationships, even randomly, and then collect and diffuse energy, so you can see what is often traversed in my vicinity, what are the most influential points in my network, and so. And then you have exhaustive algorithms that are often used in for instance, special applications, or even like brute force applications, like the Dijkstra, the breadth first traversal, A-star, shooting star, that are more directed traversals if you have the possibility to do that. In financial data, there's different approaches to graphs. You have, for instance, fraud detection, which in a sense is pathfinding through a network. In this case, from an ATM withdrawal, you want to see, is there a connection to the Godfather that's over here at node 1? And if there is, then alert me. That is then there's a connection between these two, and there might be something we need to do about this. Another thing is to deduct intelligence from these relationships. If you, for instance, have different accounts, and you can deduct that these are linked to the same person because they're used from the same computer, they have the same cookies and so on, then you can basically deduct that these might be linked things, and then act accordingly and treat them as one. GIS and geolocation services are very interesting data structures. They basically always, this is a figure from Wikipedia. I didn't write it here, but the copyright goes to Wikipedia. That depicts a quad tree, basically a data structure where you say that I will partition my two-dimensional space until in every quad or in every rectangle there's only one point of interest left. If you project that into a data structure that looks like a tree, that's what they're called, quad trees. Now there's of course multi-dimensional indexes, but this is like easier to show. A typical geographical structure that we have been working with a lot is OpenStreetMap. It is a good example of a interlinked graph that you have here in the left version. There's a street here where you have a number of nodes that are inserted by two users here, Grillo and Craig Taverner, and then you have change sets here that constitute these things. Over that, we build a linking structure that depicts the way and really is a traversal that says go along the first node relationship, along all the next relationships until you can't go any further, and then collect one hop deep the nodes that these next nodes are linked to, and then construct the bounding box over them. So this this thing here is really the definition of the way, and here you have the bounding box on this. Then you of course have tagging, free tagging on any level. We're not seeing here all the overlying structure of like higher order structures like polygons and polygons with holes and buildings and so on. And on the right side here you have again an R tree here that only has one level deep. It has a bounding box here that links to that node here by the geometry relationship. So with this, we can actually define traversals through any domain data structure. It doesn't have to be OpenStreetMap, in this case it is, that can find spatial structures and combine them with lookups into the domain data set. For instance, find all the ways where the tags here are highway residential or bridge or I don't know, like number of people on that street is bigger than 3. So, and then you can return that into a GIS, a geographical information system, or just back to the query as a geographical query, which is far more powerful than a simple, nearest points of interest search. So that makes really use of a graph structure. In real world, for instance, we're importing Germany into a single graph that constructs about 200 million nodes and about 20 million ways, and then a number of municipality borders and so on and so on. This is very interesting to be able to traverse these graphs dynamically for all sorts of analytics on this that are very, very easy to do. Another application of location-based services is cell network topologies. I'm just briefly mentioning these. You have basically cell towers and drive data that you collect from mobile phones, the cell data and infrastructure data. And what you want to do is to have the signal strength analytics going, and you want to have antenna placement and so on. This is a company that Craig is involved in, who's also doing much of our spatial work, that is doing very, very interesting stuff in this field. And you then can plan overlapping of frequencies, things that are very, very complicated to do without the use of graphs. So you can even diff the networks over time, so you can see how was the graph yesterday, how's the graph today along certain functions that you want to differentiate again. And of course, what you want to do is also to report and chart, which is often to project graph queries into two-dimensional queries, and then make two or more dimensional reports over that. So in practice, this looks this is a desktop application based on Eclipse, and the data here is a number of million nodes that drive data. This is very, very dense data, indexed both in time and in spatial. And then you have the data around it here that is, for instance, the cell tower networks, and the background data that might be all the points of interest in Germany that you run live simulations over. So here we have actually three views of the same graph structure. You have here a hierarchical view over the antennas in Aachen in Germany. You have here antennas and cell towers, and you have here antennas that have a certain orientation, which is highlighted here. And then you have the graph view on that, which is really like a child relationship. Here, along the child relationships, from Aachen down to the tower, down to the other antennas. That's the view that you see here at the side. If you look at this here, the next relationship, that is used to index these things, the towers as points of interest in the R tree. You see here the index-child relationship that points to an index subtree with bounding boxes here. So that's the indexing substructure. And then, of course, you have this spatial component here. So if you intersect the drive data and the antenna data, then you get a graph that really displays with the underlying data from, in this case, OpenStreetMaps, how the signal strengths are between the different towers. So these are, and you can do this in time and with color coding, how much signals these are. Actually, the color codings are indexes in themselves, again, that gets inserted into the graph. Another very hard problem that is frequently coming is routing. Routing is not only like in spatial applications, but even in logistics. How do I route a package through different stations? I can fly, I can ship by car, I can ship by train, and then I have different stations which might be different stores where I can have the goods in a different long. And what I want to do is to optimize these things in both time and in cost, of course. So you have quite complex cost functions when you go from start to finish. This is like a special routing. There's actually a number of projects built on Neo4j that are doing routing. And one interesting approach that might be good for you to know is to actually combine the live graph routing with the pre-calculation. So you actually calculate the possible graph routes from a station to all the other possible stations in advance, and then you do live routing on only these, so you don't need to examine all the possibilities in the network if you are at a given point, but you can actually have a little subgraph that points to the possible routes that you can have, and on that you can have live conditions like weather or cost or time or something. So you can have a combination of kind of pre-calculation and live calculation on the graph. Of course, simulations are very interesting. In bioinformatics, for instance, the focus is on offline calculations on big data. This is something that came up on the user list, and an energy kind of Monte Carlo simulation over Europe. The same thing goes for financial forecast simulations, where you change different variables and nodes, and then you model how things are interlinked on the stock market, or on weather, or in bioinformatics or others. So here you basically change factors of price and agents and so on, and then you make visible, or you just extract different ways of extracting a key data point and see the volatility on things. In this case, you actually can see that this is more volatile than these knobs here if you change certain data, which is kind of cool because it's a very, very big graph and it's visual. Summary. We see graphs increasingly being used for real-time transactional data that is to be processed on live loads. And the pattern we see is that you transform write load in the database where you have a lot of duplication that you want to make in order to be able to handle your read load, or that you combine business intelligence and analytic approaches, or OLAP queues, into Neo4j into the critical path and live data. So that is one big thing. The other things, of course, developer convenience. It's very, very easy to develop with Neo4j and with graphs, which also makes for very interesting scenarios where you fast can do complex applications. And much of the value in today's applications is not only in the amount of things that you do in the application, but what you do with the data you collect, and complexity and handling deep queries that you can't do otherwise is a big part of that. And to be able to do this very, very easily is a key driving factor of graphs. Beside the fact that they are as ubiquitous as a relational model, without any big trade-offs on the variability of data. So I think I'm done here with my little run through. I would like to take questions from you, and also it would be very, very cool if you could tell the community and others how you use graphs and what you see as the key drivers, because that's very interesting to know for others to start using this. If you found it, if you find it useful to use Neo4j and to use graphs, it would be very interesting to know why you find it useful above all.
Okay, Peter, we have several questions that people have asked, and so I'm going to read them off to you right now. The first question is, if you're using an embedded database, how is the high availability setup configured? I.e., is an embedded database basically a file, so how do you split it into many servers? How does the clustering work in this scenario? Is it done at the file system level, or what?
Now, the high availability and clustering is done not on file system level, but behind the Neo4j API. That means every node of the cluster or database part of the high availability cluster has a network connection both to the underlying zookeeper cluster or, for instance, other discovery mechanisms and the other nodes in the cluster, above all the master. So what is actually going on is that you configure, as part of your graph database setup, you configure ports where the zookeeper cluster is listening. That's basically what you need. And from there, the other instances in the cluster will be discovered. So what happens is you write to your local embedded graph database, which takes, before writing to disk, it makes sure that there's a master, that the master ships over the latest data, if that is so, and if the if the local database has already a log taken, which is the latest one, then it doesn't need to acquire a new one. If there is someone else, it requires a log, it writes and ships over the data and then commits. After that, the master database is rotating its logs at regular intervals and then doing updating of the other read nodes in the cluster. So it's very transparent from the application point of view because it's implemented below the Neo4j API. So you can just code away in Java or JRuby or even in the server with whatever you want, and it's transparent at that point.
Thank you. The next question is, how is security managed in Neo4j?
Security on the node level is not managed at all because there's different scenarios, and what we see is that security very, very often, or like in 90% of the cases we see, is managed at application level. Neo4j being part of, for instance, a Rails or Django application or a Spring application is expected to leave the security aspect to the application when it comes to what data can be accessed. Now, when it comes to the file system, of course, you can use the whole data security framework to secure like encryption and that kind of things. In the server mode, security is again on an application level, so you secure URIs and URLs that you can access or cannot access. If you ship code to the server, you need to make sure that the code doesn't have excessive security permissions. For instance, if you execute Gremlin on the server, you want to make sure that you have a Java security manager that disallows, for instance, file access for this. Otherwise, you could send over a Groovy script that says, remove everything from the root down. That is something that we are very careful with, which is why we are not super promoting server plugins, which are highly useful, but they are also very, very powerful. We will probably in another webinar say more about the Neo4j server, the Tinkerpop Gremlin projects, and all that ecosystem of traversing. But the pattern of having kind of application level security and then the data handled by the application, the data security, is quite common for NoSQL databases because the overlying stacks nowadays are very, very powerful.
Okay, thank you. The next question is, how is the performance in applications with many inserts and updates to the graph database?
That depends mostly on your hardware and your configuration. In principle, if you run transactional, the performance is mostly limited by your I/O speed on disk. If you commit a transaction right now, data will be written to durable to disk, which means I'm having a Joan behind me here who whispers in my ear, and that means you have to hit disk. So SSDs are of course much more beneficial than spinning disk. We are in the process of looking into other more relaxed models where you, for instance, can have durable transactions that are written by the file system and that don't require you to flush, which of course increases the performance a lot. So the data will still be consistent, but you actually might lose the last transaction or some minor data, but the data will be recoverable and persistent. So you can choose per transaction how durable and how persistent you want to be. During insert scenarios, that is very, very beneficial to just pump in data and not compromise the transactional and full cacheable Neo4j implementation. Right now, there is non-transactional inserts in the storage format, which is very performant, but of course not taking advantage of the caching layers and the transactional security. So if anything messes up, then your store is corrupt. So this is only recommended for insertion of insert of data. So we're working on improving this a lot with transactional semantics.
Okay, another question. Neo4j is JTA compatible. Oh, JTA capable, sorry. Can it be used with Spring and add transactional annotations? Does it work with Atomicos?
It does. It does. We are fully JTA compliant. We even are so compliant that we are having our own transaction manager that manages all the indices and the Neo4j data store itself as different XA resources. So what you can do is to replace this transaction manager with Spring Transaction Manager or JBoss or Atomicos, and by that let Neo4j and all these sub-data stores participate in that transaction. That means also that we have a recovery log and recovery capabilities on XA resource level, which is the indices have their own recovery mechanism and the data store too. We are thinking of a variant where the whole Neo4j database system is acting as one XA resource, which would diminish the need for separate durable transaction logs per transaction. But that is something that we are contemplating because it would increase performance, but it would put up the granularity of your transaction framework to the Neo4j whole system level.
Okay, I've got one last question as we're running out of time here. What are the plans for RDF triple stores in Neo4j? I don't even know what RDF triple stores are.
Yes, RDF triple stores are supported in two ways. We have been writing, actually the first system that ran on Neo4j after it was open source 2007 was a semantic system. So there is RDF support for Neo4j in the Neo4j components. Lately, there is much younger, a more up-to-date but less tested triple store or RDF support via the Tinkerpop layers, where Yoshi Navier has been writing a very nice adapter. So we are having that tested, and we would like people to report back if it works good. We are not saying that is production grade yet, but it has of course potential. It does use indexing, so there might be. We have to test performance on this first, but it's a very promising approach. In principle, there's several ways to make a Neo4j implement the SAIL API. Yes.
Okay, actually, that is all the time that we've allocated for this webinar. I'd like to thank Peter for helping us with his expertise today. I'd also like to thank Jean for giving us some of his experiences using Neo4j. And I'd like to thank everyone that has stuck it out for this hour. We appreciate your attention. I know that you'll have more questions about Neo4j, and I invite you to go to the www.neo4j.org website, where we have a very active mailing list discussion group. And if you post additional questions there, I'm sure that they will get answered in detail. We have made a recording of today's webinar. Once it's uploaded to our servers, we will post it on the www.neo4j.org website, so you'll have access to it in the future. So thank you, and goodbye for today. Thank you, Peter. Thank you, Guillaume.
Thanks, everyone. Have a nice day.